Before we go on to quantitatively define the change in entropy for a system, and we're going to do this both from a microscopic point of view, that is what we've just done, molecule by molecule, and a macroscopic point of view, because we'll find that when we look at the determination of the change in entropy, one of the most fundamental aspects proving that we in fact have the correct expression for the change in entropy is to come in from the molecular point of view and then come in from the macroscopic ensemble point of view and demonstrate that the same result comes from either the microscopic or the macroscopic approach. But before we do that, we need to look at developing intuition about the sign of delta S, because when you're working a problem in entropy, the first thing you want to look at is to determine whether entropy is increasing or decreasing. And to do that, we're going to look at 4 different changes. One of them is changing the temperature of the system. The second is changing the physical state, that is going from a solid to a liquid to a gas. A third is this issue of releasing molecules from one domain into another. We've already done that, by the way, when we looked at the initial and final states of our 10-molecule system, where we opened the valve to determine the number of microstates in the final configuration versus the one in the initial configuration. And then finally, we want to look at the sign of the change in entropy for a chemical reaction. So let's walk through these because they're extremely important. So let's consider a crystal at 0 Kelvin, absolute zero. A pure crystal at absolute zero is profoundly organized. It's locked down. There's no molecular motion whatsoever. It's motionless. And in a perfect crystal, it turns out that the entropy of that configuration is 0. We'll see why that is, but the entropy in that particular situation of a perfect crystal at 0 Kelvin, the entropy is 0. Now, if we increase the temperature, that means that we have put heat into the system, and when we put heat into the system, it begins to raise the kinetic energy of the molecules within that system. And depending on their structure, this could be translational energy, it could be rotational energy, it could be vibrational energy, but the motion that's intrinsic to that gain in heat actually goes into increasing the disorganization of that crystal structure. So that oscillation, that movement of the molecules represents an increase in disorganization, and that's why the change in entropy is positive. It's increasing. It's increasing toward a state of more disorganization. As I put more heat into the system, these molecular vibrations become more and more violent. The separation becomes larger. The intrinsic motion amongst and between these molecules increases, and it becomes increasingly disorganized. And that's why if I increase the temperature going into any system, it doesn't matter if it's a gas, a liquid, or a solid, the disorganization will increase, and so too will the entropy. Now let's look at the predicted sign for the change in entropy when we change phases. So in this case, let's look at the solid phase first, and let's just pick our favorite solid, ice. Ice is a beautifully structured molecular configuration of water combining into a crystal form, which is transparent. We know that that's ice. And that's a highly organized form of matter. And if we melt that ice, we're moving toward the liquid form of water. Now, the liquid form of water is distinguished from the crystalline solid form because those water molecules can move past one another, around one another. They can exchange energy. And they're starting to pick up vibrational and rotational energy, which is allowed within the structure of a liquid, but not within the structure of a solid. So as we go from solid to a liquid, the degree of disorganization increases significantly, and that means that the change in entropy is greater than 0. We're going from a more organized state to to a less organized state. And then finally, let's put in so much heat that we evaporate water from the liquid state to the vapor state. Now we've got molecules that are essentially independent of one another. They're not bound together, but they're colliding with each other. They're exchanging energy very, very rapidly. But that state, that gas phase state, is vastly more disorganized than was the case with a liquid, just as the liquid is vastly more disorganized than a solid is. So again, that gives us an increase in entropy because we're increasing the degree of disorganization. So let's turn now to the case where we are releasing molecules constrained on the left-hand side by removing a diaphragm between the left-hand side and the right-hand side. And this is exactly equivalent to what we did when we turned the valve on that two-bulb system, allowing 10 molecules to go from the left-hand side to the right-hand side. And we know when we did that we could calculate the change in entropy, which was equal to the Boltzmann constant times the logarithm of the final number of microstates divided by the initial number. But to determine the sign, we can do that without doing the calculation, because when we look at the situation, those molecules have moved from a sequestered corner of that total volume to distribute themselves evenly throughout. That is, the degree of organization has changed significantly. The final condition is far more disorganized than was the initial condition. And the easiest way to look at that is to run it backwards. If you're going to take all the molecules that are in that volume, shown under C on the right-hand side, and move them back into just the left-hand side, you can see that that's a condition that's far more organized than the even distribution of molecules throughout the system. Finally, let's turn to a chemical reaction. Now, we saw when we burned gasoline that C8H18 reacting with oxygen formed CO2 and water, and there were far more molecules of CO2 and water on the right-hand side, the product, than there was in the initial reaction of gasoline plus oxygen. So in that case, the degree of disorganization increased with that chemical reaction. But let's look at another case. Let's take bicarbonate of soda. And this is a very famous compound because it's used in cooking. And it's used in cooking because it starts as a solid, and when we heat it, it turns into sodium carbonate, but it releases carbon dioxide and water in that reaction. That carbon dioxide is what causes that cake to rise, or that bread, or whatever it's in. So that CO2 gas forms little pockets that expand outward, and the cake rises. But more than that, the water that's produced in that produces the nice, moist characteristic of a good cake. And so that material is extremely famous. It's been used for centuries for cooking. And if we started with bicarbonate of soda as a solid, it would be sitting down here in the bottom of this vessel, highly organized as a solid. And as we begin to heat it, it begins to release CO2 and water. And as we heat it more, all that's left behind is this very small residual powder, which is the sodium carbonate, and all the rest of it has been turned into the gas phase carbon dioxide and water. So in this case, the change in entropy is immediately obvious. The sign of it is that it's greater than zero, because we've gone from a highly organized solid molecular structure to a combination of gas phase molecules and the residual solid.